on current carrying loops. So this is going to be kind of similar to electric torque on dipole moments. So we're going to kind of relate it to that. So let's say there is a magnetic field like this. And there is a wire in this magnetic field. Wire has a current like this, current going up like this, and then across, and then down, and then to the left. So we want to see what the total force on this wire is, the current carrying loop, the total force and the total torque. So we analyze the forces on each side of the wire. So let's say this is the length from here to here is, let's say, L. And let's say this is the width, W. Okay, so on this side of the wire, the force is, we do the cross product, I crossed into B into the board. So you're applying the equation F equals IL crossed into B on all elements of the wire. So like that, into the board. Now on the top one, it's like this way, crossed into the, well, actually, no. This one, there's going to be no force because the I and the B are in the same direction. So the top, there is no force. And then this one here, like this. So it's going to be coming down. So I cross into B out of the board. And then the one that goes back is also no force. So the force on this side is going to be into the board, and then the force on that side is going to be out of the board. The two forces are going to equal because it's just going to be I, the force is going to equal I times the width times the magnetic field. So this one is on the left side, and that's into the board. And then the force on the right side is IWB out of the board. So the net force is 0. But there is a net torque. So the outcome of this, it's like taking a calculator and then taking the left side of the calculator and pushing it in, and then taking the right side of the calculator and then pushing it up like this. You see? So it causes the object, you see, when I pull this one, when I push down on something and I pull up, I cause a net torque about the center of mass of the object. So there is a net torque, and the torque is going to be equal to what? R crossed into F. Right, so from Physics 101. So it's going to spin around the center of mass. So then the torque due to the right force is going to be the length from here to here. So that's going to be L over 2, right? Half the length. So the R is going to be L over 2. And then crossed into the force, which is this guy, IWB. Right, so it's basically like this. This is the axis of rotation. This is the L over 2. And then the force is out of the board. So then you go like this. The torque is down. So this crossed into this gives you a down torque. So essentially what that means is that it tends to make the object come out of the page like this, you see. So you're pulling up, so the object rotates like this. And then the torque due to the left side is also down, crossed. You see L over 2 cross into B. It's like this. So then you have here the two torques add up essentially. Torque 1 and torque 2. So then you basically double this. L over 2 IWB times 2. And then the net torque is going to be, this is the total torque, is going to be just LIWB. Okay. So now we're going to define something known as magnetic moment, the magnetic moment of that wire.
What is the W?
It's the width. And then the L is the length. The
Okay,
W came from the fact that the force on each side is based on the width, the length of that. W came from there, but then the L came from the fact that the torque is R crossed into F. And then so you have LW. But then LW is the area, the surface area of the wire. So I can now define something known as magnetic moment, which is I times the area. Okay. And if there's n number of turns of the wire, so if it keeps looping around, so then the torque is going to be NLIW. So then the magnetic moment can be defined as NIA. So if it's a vector, it also has to have a direction. So the direction of that is going to be in the direction of the area vector. Okay. So this is definition, essentially. 3 lines means definition. So magnetic moment is going to be amp meters squared. So magnetic moment is a description of how this coil of wire reacts to an external magnetic field. The stronger the magnetic moment is, the quicker it reacts and the faster it spins, you see. In other words, the torque on it is greater. And then the equation for the torque is going to be what? The cross product of the magnetic moment into the magnetic field. Okay, so now let's practice that, see if this makes sense. What's the direction of the area vector in this case? How do we determine the direction of the area vector? Well, we take a look at the direction of the current flow. The direction of the current flow is clockwise, right? It's going this way. So then we curl our fingers in the direction of the current flow, and then the thumb points into the board, you see. If it was counterclockwise, then the area vector would be out of the board. But if it's clockwise, you go like this, the area vector is into the board. So that means the magnetic moment of this loop is into the board in this case, right? So mu is into board. And in our case, what's the direction of the B? Okay, well, it's to the right? So then based on that, if I do the cross product of mu and B, what's going to happen? So B is to the right. And mu is into the board. So now take the cross product of into the board. So you're doing 2 right-hand rules here to determine this. First, you're doing the curl your fingers in the direction of the current flow. Your thumb points in the direction of the mu vector. Then you're taking the mu vector, which is into the board, and then you're crossing it into the B. You know, like this. And then your thumb points in the direction of the torque. Okay, so the torque is down. So the vector that's into the board, cross product into the B, the torque is down. Well, that matches the answer that we got by analyzing the forces, you see? So I'm doing the check to see if my definition of mu yields the correct direction of the torque. And it worked, you see? Because based on simply just forces, R crossed into F, we already determined that the torque is down. This torque is also down. So we already knew that the torque has to be down. And so when we did this check, we get the torque is down. But more important than the direction of the torque is the direction of rotation of the coil. How is it going to rotate? Well, it's going to rotate like this. Let's see, is that true? Yeah, like this. Right? And what does it want to do? It wants to, eventually it's going to rotate so that it looks like this at the end. The B is like this. So this side is going to be coming like this. This side is going to be facing us, right? Like that. What's the direction of the current flow of that side when it finally like this twists and faces us? So what was the direction of the current here? It was going like this, from up to down. So when it finally faces us, this side, the current is going to be going like this, right? Then on the bottom, the current is going to be going into the board. And then from the other side, it's going to come up. And then it's going to come back out. Do you see? So then when that's the case, if you want to do a 3D drawing, you would go like this. You see? Like that. So the current goes like that, up, out of the board, and back down. What's the direction of the mu there? Okay, so then you go like this, you curl your fingers. You see the direction of the area vector, you curl your fingers in the direction of the current flow, which is going like this. And then the mu vector faces to the right, you see? Aha, that's the direction, the preferred alignment. That's the preferred alignment of a magnetic moment with an external B field. The mu wants to be lined up with the B, okay? So therefore, that's basically the way it works, is that if we write this as mu crossed into B, then the perfect alignment will happen. Of course, the thing won't just stop there. So it'll start like this, it'll go like this, and then it'll oscillate, you know, like that. Simple harmonic motion like that. So then the potential energy equation is negative mu dotted into B. So the most minimum potential energy of the magnetic moment is when the magnetic moment is lined up with the B. That gives you minimum potential energy. So now it's nice to kind of make an analogy with electric dipole moment, right? So you can say, back in the previous chapter when we did electric dipole moment, you have the E field like this. And then you say, okay, if you have a charge like this, and another charge like that, that is bonded together, right? So then you can say there's a force on it this way, QE, and then there's another force on this guy, negative QE. So dipole moment is one where you have a negative and a positive charge bonded together. So you have two forces. Similar things are going to happen to this case. The forces are going to cancel. So there's going to be no net force on a current carrying loop, just like there was no net force on a dipole moment. So the dipole moment doesn't translate left and right, and this doesn't translate out of the board into the board either. It stays in place. but there's a net torque here. So the torque is going to be with respect to the center of mass. So it's going to be this distance, call it A. It's going to be A crossed into F, A, Q, E, right? And then that's going to be into the board. So the torque is now into the board. And now this guy is going to be another torque. A crossed into B, also into the board. A, Q, E. So the torque, both of them are into the board. So a similar derivation. So here you're doing R cross into F, where F is the force on each segment of the wire. Here you're doing R cross into F, where you're doing the force of the electrical field on each charge. Then you're adding them up. So you're getting the net torque into the board. Then you're defining something that comprises all these together. You're calling this electric dipole moment. Electric dipole moment, P, defined as 2AQ. And then the direction of it, you have to define it in such a clever way that when you do the cross product, so once you define it this way, you have to determine what's the direction of this vector. So then you have to do it in such a way that when you apply the equation P crossed into E, that you get a vector into the board. Do you see? So how do we define P? And what they do is they define it as a vector. 2A is the vector, the total length between the two charges. So they define it as R hat vector, where it's from the negative charge to the positive charge. So the R hat vector is going to be from the negative, is going to be the origin, and then it's going to point towards the positive charge. So now if you do the P vector points this way, and you do the cross product into the E, okay, P cross into E, into the board, you see? So that matches. So definition of P is 2AQ R hat. Definition of mu is NIA, where A is the vector curled around the current and the thumb points in the direction of the current. Then you say potential energy is negative P dotted into E. Okay, so now what's going to happen to this charge? What is its preferred alignment? So this charge is going to be spinning this way. This charge is going to be spinning this way, so that final alignment should look like this. Right? Like that. And then therefore, when it's lined up like that, you have the E, right? And when it's lined up like that, that's when it's got the least potential energy. You see, so potential energy is equal to minimum is negative PE when the dipole is lined up. But of course, it's going to pass that point, and then it's going to start spinning like that, make harmonic motion. And same thing's going to happen to this. The minimum potential energy will occur when the dipole moment is lined up, right? When the mu is lined up, or when you could say when the surface of the cross-sectional surface of the coil is perpendicular to the B. In other words, the magnetic moment faces in such a way as to maximize the magnetic flux through the coil. You see, the magnetic flux through the coil, that's its preferred alignment, like that. So